Hello, everybody. My name is Leah, and me, Sienna, Mehiret, and Aeron are going to be talking about the impacts of Greenland's ice sheet stability and deglaciation in the 21st century. Next slide. So first off, we're going to be talking about Arctic amplification and the warming trends in the Arctic Circle. So the warming trends of the Arctic Circle on a 43-year frame are faster than 0.75 degrees Celsius per decade, which is 3.8 times on a global average. In figure C, you can see how the local amplification is 7 times on a regional focus towards the Eurasian sector. And figure B reinforces what's going on in figure C, showing the temperature trends in similar areas of the local amplification from 0.75 degrees Celsius per decade to 1.5 degrees Celsius per decade. This is thought to be due to the decreasing albedo and the distribution of landmass in the northern hemisphere. Next slide. So we're going to be talking about loss of ice cover and mass melting. So due to the rising temperatures, it causes increased surface melting. In this in this figure, it shows how the Arctic was originally had a lot of ice, and over time, as the ice melts, it shows the decrease in ice. The meltwater reduces the ice reflectivity, which is known as the albedo effect. And as water seeps into the cracks, it speeds up the glacier movement, and warmer oceans melt ice from below, which shows in the figure how the ice was originally built up and there was more ice than in figure B, which shows the decrease in ice and how more land is showing up compared to ice. Next slide. And in this figure, we can observe that the ice loss is slowly going down over time. And even if the temperature goes back and decreases instead of like warming up, even though ice melts, even though ice builds back up, it's not going to be as similar as it was originally. Greenland is losing hundreds of billions of tons of ice per year, and the ice loss has accelerated since the 1990s. The Arctic Sea ice declining is the extent and the thickness, and the mass loss is increasing over time. So no matter if the ice ends up building up, it's still not going to be how it was originally. So because of this warming, it is really impacting the land because of the ice constantly melting and not reforming as it was originally. Next slide.
Okay. Our next slides are going to be talking about future predictions, not only on the Greenland ecosystem, but also on people. And in this slide, we're going to talk about how this is impacting Greenland and the ice sheets. So as temperatures continue to rise, melting ice increases, pushing the Greenland ice sheets towards critical tipping points. This graph on the left shows how the ice sheet responds to temperature change, with temperature on our x-axis and the volume and sea level rise on the y-axis. At first, the ice sheet shrinks gradually, but our paper identified a critical transition at around 1.6 degrees Celsius of warming, where there's a sharp drop in ice volume indicating rapid ice loss. This suggests that once the threshold is crossed, the system can shift quickly towards collapse, and it basically gives us this moment of us being unable to shift and Greenland never being able to grow back that ice volume that is lost. The graph also shows us how the different paths there are for warming and cooling temperatures. So that is highlighted by the red and blue points. This demonstrates hysteresis, meaning the ice sheet behaves differently depending on the direction of climate change. So even if the temperature begins to decrease, the ice sheet does not immediately regrow. It stays in a reduced state and requires a lot cooler conditions to recover to its original state. So overall, continued warming leads to faster melting, the risk of crossing irreversible tipping points, and a system where Greenland ice sheets cannot return to its original size as quickly as it was lost. Okay, so how does this impact the ice loss and the ecosystems around it? Rising sea levels are causing increased flooding and coastal erosion, putting homes and communities at risk. At the same time, melting ice is leading to the loss of Arctic habitats, threatening animals like polar bears and seals that depend heavily on ice for survival. These changes also disrupt our ocean circulation and ecosystems that live within the oceans near the Arctic, affecting weather patterns and marine life around the world. Next slide. Okay, and then finally, how does this in fact impact people? So coastal communities are high are at high risk as sea levels continue to rise, leading to more frequent flooding and serious damages to homes, roads, and infrastructure, and also increased in natural disasters um, caused by the increase in temperature. A recent example is this small, low-lying city in California where rising sea levels are already causing flooding from both the ocean and groundwater, forcing officials to consider expansion protection plans and possibly relocating people. This not only threatens safety, but also creates major economic costs, forcing many people to relocate and leaving communities struggling to recover. Over time, these impacts expand beyond local areas, contributing to a long-term global consequence for economies, ecosystems, and populations worldwide, leading to large migration patterns.
So now we're going to go deeper into the specific mechanisms that cause this destabilization of the ice sheet. So the first mechanism we're going to talk about is called subglacial erosion. This happens when the melt on the surface of the ice sheet travels to the base of the ice sheet through these tunnels called moulins. And this lubricates the base of the ice sheet, causing acceleration of the ice flow towards the margins, which you can see in the red. You can see in the graph over here, you have the moulin circled in red. It leads down to the base where there's an arrow showing it lubricating the base. And then you can also see in the yellow box how it's causing this acceleration, it's speeding up. And what happens, therefore, is that it ends up eroding the underlying bedrock through the subglacial streams, which ends up ungrounding the ice. In figure A, you can see how these create subglacial tunnels below the glacier. And then as these channels erode the bedrock, it's eventually going to lose the ground underneath the ice sheet, and it's going to cause it to be ungrounded or make it unstable so that the ice is now floating on top of the water. And then the second mechanism is through warm Atlantic waters. This happens when the ice sheet becomes vulnerable to warm Atlantic waters as the ice is now directly meeting the margin of where the ocean is. And so these warmer waters at greater depths, they end up undercutting the ice and ungrounds the ice flows. So as you can see in the four identified mechanisms, um, you can see how the warmer regions below, they end up undercutting the ice because it's so much warmer. It's going to remove ice from underneath the surface of the ice. And so it's going to end up having a larger area that's going to be floating. And the four major mechanisms going to be a glacier in a deep fjord, with warm water. There's going to be one where it's on top of the calving ridge. You can see how the ridge is protecting some of the glacier from that warmer water. We have the shallow fjord and cold water, so it's not really interacting much with the warm water. And then lastly, you have the long floating extension where you can see that it's undercut so much that you now have like a long floating ice shelf over top of the warm water. And these different mechanisms all vary in count and effectiveness, as you can see on this next slide with additional data. So you can see in the red box, that the shallow, not the shallow, the deep, that the glacier in deep water is going to have the second to most number of glaciers in that category, and it's also going to have the most effect in terms of losing ice. It's going to have the most ice loss, most discharge of meltwater, and also the largest contribution to the mass balance with a loss of 66.3 gigatons per year being lost. And then you can also see how the shallow cold glaciers, that's going to be contributing the least to the mass imbalance, which can be expected with only a loss of 6.7 gigatons per year. And then you also in the yellow box, you can see the other two categories that weren't really mentioned. That's going to be the sustained retreat, those luckily are there aren't many of them, and they don't contribute too much to the mass balance because they've already retreated so far. There's not really much left to retreat. There's not really much ice left to lose, and it's also you can't really get put into any of the other categories because it's already long since basically eroded away. And then the last thing, the part of this label NC, that's uncategorized. And so luckily it's has the most number of glaciers in it, but it only contributes moderately to the mass imbalance. And then as you can see in the map on the right, it breaks up the Greenland into 7 sections where you can actually see target all these different glaciers, and you can view the retreat area, the specific mechanism affecting it. And then also for the most interesting one is for the deep warm glaciers, because that's really where you're having the most mass loss. Those ones, it also creates a pie chart showing how much of it is being undercut and how much has been calved. Undercut, we've already discussed, but calved, we're about to discuss in the next bit. So the importance of grounding is that um, both the subglacial erosion and the warm Atlantic waters, they unground the ice, which just means that you're not don't have that stable ground underneath it. And so the ice is going to end up floating over top of the water. Then when this happens, it's going to make it unstable because now it's going to be susceptible to stresses from different tidal stress from the tides. And so it's going to be moving it up and down, accelerating mass loss by calving it into glaciers. And all calving really means that's going to be breaking the ice sheet into glaciers and break off the mass from it. And this will worsen as temperatures and sea levels continue to increase, affecting how much the Atlantic water is going to be affecting it, and also accelerating the erosion as the sea levels rise.
Okay, for these last few slides, I'll be talking about a 2023 study that used dating methods on Greenland sediment to simulate the effects that an interglacial had on its ice sheet. I'm specifically talking about marine isotope stage 11, which was an interglacial period that occurred around 400,000 years ago with prolonged warmth. And this warm interval lasted around 29,000 years and reached peak atmospheric CO2 levels of 286 parts per million. Now, although the warmth and CO2 levels were moderate, there was a large-scale retreat in the northwestern and southern parts of Greenland's ice sheet. Next slide. This study collected subglacial sediment from Camp Century, a scientific research base in Greenland, which you can see is on the top left of the map. And to the right, you can see 3D model renderings of recent photographs of this sediment. And this study looks mainly at sample 1059-4 on the top right. And it was analyzed using 2 dating methods to model the maximum possible duration of surface exposure of the sediment. Next slide. So I'm not going to go over these in too much detail, but one of the methods that was used was luminescence dating. It's basically a dating method which is used to determine when mineral grains were last exposed to sunlight. And basically, this study found that the sample was last exposed to sunlight around 378 to 454,000 years ago, which was during the MIS 11 interglacial. Next slide. Now, the second method that was used was cosmogenic nuclei dating, which looks at isotopes that form inside quartz when sunlight and cosmic rays hit the Earth, hit rocks at Earth's surface. Now, basically in figures A and B, they modeled aluminum 26 and beryllium 10 ratios at different exposure times in kilo years before the sediment was deposited back into Earth. And they found that the surface exposure was no longer than 14,000 years. Next slide. So the dating methods I just showed established when and for how long Camp Century was ice-free, which provided the team with constraints for modeling ice sheets. So the study ran 96 simulations to find what results in an ice-free Camp Century, and 79 out of the 96 hypothetical interglacials resulted in deglaciation at that site. And the simulation with the least amount of ice loss resulted in 1.4 meters of sea level equivalent, and near complete loss of Greenland's ice sheet resulted in around 7 meters of sea level equivalent. Next slide. So, what are the modern implications? Like, what does this mean? Well, Camp Century is located in a local ice dome in a relatively cold area with high precipitation. So, the sector of Greenland's ice sheet is resilient to warming. And since 82% of the simulations resulted in deglaciation at this site, it is implied that there will be substantial mass loss elsewhere in Greenland. So global sea level contributions are most likely going to be well above 1.4 meters, meaning more frequent floods and loss of coastal land. Also, modern atmospheric carbon dioxide levels are around 430 parts per million, which is well above MIS 11's peak 286 parts per million. So there's greater potential for more substantial and long-term ice loss in Greenland. And finally, if 29,000 years of moderate warmth during MIS 11 caused a substantial retreat of the ice sheet, then today's rapid anthropogenic warming likely increase will increase the likelihood of comparable or greater ice loss, and will also raise the chances of crossing ice sheet thresholds or tipping points sooner.
Okay. And here's our bibliography. Thank you for listening.